NENOMATICA, where mathematics meets YouTube excellence. Example: we will solve the system of linear inequalities step by step, mirroring the structure exactly as shown, and finish by intersecting the solution sets. Step 1. Use the linear inequality rule to isolate x. Then transform the first inequality line by line. 5x plus 12 is greater than or equal to 3 times quantity 1 minus x minus x. Expand the right side. Collect like terms. Move terms to opposite sides. Divide to solve for x. Finally, record the first solution set. Step 2. For the fractional inequality, combine fractions with a common denominator and clear denominators. Start from the given line. Use 15 as the common denominator to combine. Simplify the numerator. Clear denominators by multiplying by 15. Gather like terms to one side. Divide by -29 and flip the inequality. Record the second solution set. Step 3. The solution to the system is the intersection of the two sets. Intersect the intervals. Step 1. Express y in terms of x from each inequality. From 2x plus 5, y less than 7. Move 2x to the right to get 5, y less than 7 minus 2x, then divide by 5. From 3x minus 4, y less than 1. Move 3x to the right to get -4, y less than 1 minus 3x. Now divide by -4. And remember, dividing by a negative flips the inequality. So y is greater than 3x minus 1 all over 4. Combine them together. Step 2. For the solution to exist, the lower bound must be less than the upper bound. So 3x minus 1 over 4 is less than 7 minus 2x over 5. We will bring everything to the left side. Step 3. Simplify the left-hand side using a common denominator of 20. 5 times 3x minus 1 minus 4 times 7 minus 2x all over 20 is less than 0. The numerator becomes 23x minus 33. So we have 23x minus 33 over 20 is less than 0. Since 20 is positive, we can multiply both sides by 20 without flipping the inequality. This gives 23x minus 33 less than 0. So x is less than 33 over 23. Step 4. Write the full solution set exactly as bounds on x and y. X is less than 33 over 23, and y lies strictly between 3x minus 1 over 4 and 7 minus 2x over 5. Now, let's verify the solution graphically. We'll draw coordinate axes. The blue line is y equals 7 minus 2x all over 5, and the green line is y equals 3x minus 1 all over 4. The blue region is below the blue line, and the green region is above the green line. Our x condition, x less than 33 over 23, is shown by a purple dashed vertical line. The valid region is to its left. We'll test a sample point in the region to confirm. Final result x is less than 33 over 23, and y is strictly between 3x minus 1 over 4 and 7 minus 2x over 5. This matches the graphed region. Below the blue line, above the green line, and to the left of the purple vertical boundary. Great work! Example: we will solve the system of inequalities exactly following the step order seen in the provided algorithm. Step 1. Express y in terms of x from each inequality. We isolate y. The results are y is greater than 4x, and y is less than x cubed. Step 2. Combine the two y inequalities. This produces a single double inequality. 4x is less than y, which is less than x cubed. Step 3. Because y must be between those two expressions, we must have the left bound less than the right bound. So 4x is less than x cubed. Step 4. Move all terms to one side. We get 4x minus x cubed is less than 0. Step 5. Factor the left side. Factor out x to obtain x times 4 minus x squared, less than 0. Step 6. Factor the difference of squares. For minus x squared equals 2 minus x times 2 plus x. So we have x times left parenthesis 2 minus. For minus x squared equals 2 minus x times 2 plus x. So we have x times left parenthesis 2 minus x right parenthesis times left parenthesis 2 plus x right parenthesis is less than 0. Step 7. Perform sign analysis around the critical points -2, 0, and 2. The product is negative on the intervals -2 to 0 and greater than 2. Step 8. Write the final solution sets for x and y. On each valid interval, y must lie strictly between the line and the cubic. So the solutions are -2 less than x less than 0 and 4x less than y less than x cubed, or x greater than 2 and 4x less than y less than x cubed. Now, let us confirm the solution graphically. We plot y equals 4x and y equals x cubed. The feasible region is the set of points strictly between the cubic and the line, only for x between -2 and 0, and for x greater than 2 and 0, and for x greater than 2. Example: we will solve the system of inequalities exactly as in the provided algorithm. First, step 1. Express y in terms of x from each inequality using simple algebra. Show the rule. Now isolate y from the first inequality, then isolate y from the second inequality. Step 2. Because y must be greater than both expressions, it must be greater than the maximum of the two. Show that as a rule. Write y greater than the max. Next, compare the two right-hand sides to see which one is larger for different x. Set up the comparison. Clear denominators. Distribute and simplify. Rearrange to isolate x. Conclude the threshold for x. Step 3. Summarize the solution as a piecewise description for y based on the value of x. Show the piecewise rule box. If x is less than or equal to 11/4, y is greater than the first expression. If x is greater than or equal to 11/4, y is greater than the second expression. Finally, present the solution set clearly in green. Example: we will solve the system of inequalities exactly as in the provided algorithm, then visualize the answer on a graph, and finish with a clear summary. Step 1. Isolate y in each inequality. Use the rule for solving a linear inequality for y. Then write both results clearly. Step 2. Since y must satisfy both, y must be greater than the larger expression. We use the maximum rule. To find which is larger, compare 9x minus 2/3 with 2x minus 1 by solving an inequality. We multiply both sides by 3, combine like terms, and isolate x. Step 3. Build the piecewise description for the solution set. We state it as two cases around x equals -1/3. Then show the final answer. We will solve a system of linear inequalities exactly following a clear 5-step structure. First, we display the example and the problem statement. Step 1. Use the rule. Solve inequalities for one variable by isolating y. From the first two inequalities, we isolate y to right lower bounds. Step 2. When two lower bounds constrain y must be above their maximum. We compare two x-dependent bounds by solving 2x minus 1 greater than or equal to 1/2 times x plus 1. Multiply both sides by 2, simplify, and conclude the breakpoint x greater than or equal to 1. Step 3. Use a piecewise description for the stronger lower bound on y. For x less than or equal to 1, the half of x plus 1 dominates. For x greater than or equal to 1, the line 2x minus 1 dominates. Step 4. Solve the third inequality for y. From x minus y plus 1 greater than 0, we obtain y less than x plus 1. Step 5. Combine the bounds to form two systems based on the breakpoint x equals 1. We first solve case 1, x less than or equal to 1. Then we solve case 2, x greater than or equal to 1. Case 1. With x less than or equal to 1, we have y greater than 1/2 of x plus 1 and y less than x plus 1. Check the interval is non-empty by confirming 1/2 of x plus 1 is below x plus 1. Multiply by 2 and simplify to find x greater than -1. Therefore, -1 is less than x less than or equal to 1, and 1/2 of x plus 1 is less than y, which is less than x plus 1. Case 2. With x greater than or equal to 1, we have y greater than 2x minus 1 and y less than x plus 1. Check the interval is non-empty by confirming 2x minus 1 is below x plus 1. Simplify to find x less than 2. Therefore, 1 is less than or equal to x, which is less than 2, and 2x minus 1 is less than y, which is less than x plus 1. Finally, combine case 1 and case 2 to state the complete solution set. Quick challenge. Try a few sample points from each region to verify the inequalities by substitution. Example: we will solve the system of inequalities in 3 variables and present the solution exactly in the same step order as the written method. First, we write the system. Step 1. Isolate the variable z in terms of x and y from both inequalities. From the first line, moving terms to the other side gives z greater than 4x minus y plus 1. From the second line, isolating z gives z greater than negative x plus y minus 2. Step 2. Since z must be greater than both lower bounds, it must be greater than their maximum. Step 3. Decide which expression is larger by comparing them directly. We test whether 4x minus y plus 1 is greater than negative x plus y minus 2. Gathering like terms, we obtain 2y less than 5x plus 3, or equivalently, y less than 1/2 times parentheses 5x plus 3. That line in the x-y plane splits the cases. To visualize the split, we draw the x-y coordinate plane and the boundary line y equals 1/2 times parentheses 5x plus 3. Here are the axes. Now, the boundary line appears, with 2 regions labeled below and above the line. Step 4. We now state the solution in 2 cases depending on the side of the line. Case 1. For y less than 1/2 times parentheses 5x plus 3, the stricter lower bound is z greater than 4x minus y plus 1. Case 2. For y greater than or equal to 1/2 times parentheses 5x plus 3, the stricter lower bound is z greater than negative x plus y minus 2. Summary. We isolated z from both inequalities, noted z must exceed the maximum of 2 linear expressions, compared them to get the dividing line, y equals 1/2 times parentheses 5x plus 3, and finally wrote the answer as 2 cases. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.